Newton's Apple is made possible by a grant from 3M, the company where creative people find ways to make our world even better. 3M, innovation.
Hi, I'm Sujin Pak. Welcome to Newton's Apple and our salute to engineers. Engineers use science and technology to solve problems and turn ideas into reality. They contribute to our safety, our comfort, and our everyday lives. Consider transportation, for example. Is there science in getting products to consumers? Well, if the materials are moving via barges and riverboats, there is. A river is always changing. Peggy Knapp went to find out if they could be made more predictable. See if you can spot how engineers contribute to smoother waters.
The mighty Mississippi River flows 2,552 miles from its source in Minnesota to the Gulf of Mexico at a rate of 100 trillion gallons per year. The vast strength and scope of the Mississippi make it an ideal transportation link, but harnessing the river's power has not been an easy task.
Any fan of boating will tell you that navigating on the river has its challenges. During periods of shallow water, it's not hard to, say, end up run aground, for example. That's why engineers throughout history have worked on methods for controlling the river's currents to help boaters avoid hazards like these.
Shallow water was a major problem on the upper portion of the Mississippi until the U.S. Army Corps of Engineers constructed a series of 29 locks and dams from Minneapolis to St. Louis. These navigation dams keep at least 9 feet of water in the river channel so that large commercial towboats and barges can safely travel the upper Mississippi. To learn how a navigation dam works, I toured a site with engineer Bonnie Montgomery.
A navigational dam's purpose is only to control the river levels during low flow. It has two parts. It has the lock, which allows the traffic or the boats to pass through, and it has the dam part, which controls the pool levels upstream of the dam during low flows.
Most of the upper Mississippi navigation dams are made up of a series of concrete piers with movable gates between them. Raising and lowering the gates controls how much water flows through the dam.
When you start controlling the flow, what effect does that have on the river?
As we lower the gates, we create slack water pools upstream, and during really low flows, extremely low flows, it's more like a lake upstream than it is a river.
Instead of flowing in a slope, the river becomes more like a stairway of lake-like pools when the gates at every dam are lowered. Under high water conditions, the gates are raised completely out of the water. The river then flows freely through the dams, and the water surface returns to a natural slope. Every day, engineers monitor the river flow and calculate how to position the gates in order to maintain the proper water level. The adjustments made on the 19 gates at this dam are supervised by lockmaster Frank Ewell.
Okay, let's say I have to lower that gate a little bit. There's too much water going through. How do I do that?
Well, then you would simply walk over here and hit the lower button, and then you would watch your gauge. When you've lowered 2 feet or whatever you're over here to do, then you would hit the stop button and stop.
Oh, that's the gauge I'm looking at?
Right.
Okay. So I just push the lower button?
Right.
The button starts a motorized drum. This unwinds the chains, which slowly lower the 30-ton gate into the water.
How much water am I going to be controlling by cutting that down 2 feet?
Well, 2 feet today would be going about 1,800 cubic feet per second.
I'm doing a lot with this water. I have a lot of control about this water.
Well, that's what we're here for. I mean, that's our purpose, is to maintain this 9-foot channel.
The water level drop, or head, at each dam poses an obvious obstacle for traveling boats, so locks were built to act as elevators that carry boats from one pool level to the next. I visited a dam with a 38-foot head and gained a new appreciation for the boost that locks provide. I got a chance to take over the controls, and Lockmaster Joe Dvorak showed me the basics of lock operation.
And you're doing just great. Gates are moving.
Now, is there a way I could do this wrong?
Joe assured me that the beauty of the lock design is its virtually foolproof simplicity. The lock gates were built in a miter, or V, facing into the river current. If there's a head upstream, the pressure of the higher water will keep the gates closed, eliminating the risk of letting water through accidentally.
Okay, now what will this barge do?
Okay, now you need to let him know that we're ready. So you give him a green light, lower green, downstream green, which tells him we're ready to lock through.
What happens next is really just simple hydraulics. A boat traveling downstream enters the lock when the chamber is full. After the boat is inside and the gates are closed, a valve is opened to release the water through a system of pipes and into the lower part of the river. No pumps are required. The force of gravity causes the water to seek its own level, meaning the water stops draining when it matches the level in the lower pool, and the boat can then continue on. So what happens when you're traveling upstream? Joe let me experience it firsthand.
Looks really great from inside.
Oh, yeah.
I mean, it's really impressive.
An upstream lockage is the same process in reverse. Once we were securely inside the chamber, an operator opened a valve on the upstream end of the lock to let water in from the upper pool. Remember, the water isn't pumped in. This floating elevator runs on gravity. Filling or emptying the lock usually takes about 15 minutes. That's pretty fast considering that the chamber measures 56 by 400 feet and holds about 6 million gallons of water. The dams have brought positive changes to river travel, but they've also had a big effect on the river ecosystem. The land next to the river, called the floodplain, was once flooded only during high water periods. Now much of the floodplain is backwater area, covered by water year-round. I visited a backwater site with biologist Dan Wilcox, who explained some of the environmental issues.
Well, there's an accumulation of silt in the backwater areas. The current velocity slows down and the fine-grained silt in the water column has a chance to settle out. So it builds up in these shallow places like this. So I'll show you some. Here's some real Mississippi River mud.
Oh boy, it sure is.
This silt is mostly soil that has eroded into the river. The buildup of the silt reduces water area needed by fish and waterfowl. In response, environmental agencies are building projects for improving habitat conditions for fish and wildlife.
We're building islands in windswept places like this to reduce the wave action. And
Why is wave action a problem?
well, the waves stir up the sediment and make the water cloudy so light can't penetrate, and that limits the growth of plants.
Uh-huh.
We're also dredging out certain backwater areas to make deep water habitat for fish.
The Mississippi River has been an important means of transportation for hundreds of years. The system of locks and dams on the upper Mississippi has greatly improved navigation, but it's also altered the river's environment dramatically. The next challenge for scientists is to improve methods for managing the river so that it will continue to serve the needs of both humans and wildlife in the years to come.